Okay, so we are going to be looking at the one-dimensional diffusion equation. So the setup is going to be we have like a tube and there's something flowing in it like smoke or not flow there's like a concentration of smoke in it and we want to see what happens as time goes on. It could be heat in a rod or things like that. So it's going to be a one-dimensional thing, meaning the flow there's going to be a concentration of something and it can only flow backwards and forwards. It can't, flow up and down and left and right, just flow backwards and forwards. So what are the sort of things that can be modeled by the diffusion equation? We'll say a little bit more about this in just a moment, but basically it's going to be stuff that diffuses. So in other words, stuff that just kind of will spread out. So this could be like food coloring. Food coloring in a glass. Okay, of course, that's not one-dimensional. That's two-dimensional, but same idea. Two, this could be heat in a rod. That's a popular choice. It could be something like the amount of salt in a lake. Or it could be something like a pollutant. In a lake. Okay, so just anything that's going to spread out. Like you put a drop of food coloring in a glass of water, you know how it's going to kind of spread out. It's going to spread from the higher concentration areas to the lower concentration areas until everything's kind of equal, then it's not going to move anymore, right? When you drop food coloring into a glass, it all turns the same color. Eventually, it's not like you're going to, it's not like it comes back together. Or there's part of the glass where there is no food coloring and part of the glass where there is food coloring, at least for long values, for big values of time, as time for long term. Okay, so let U of xt, this is going to denote the concentration. So this is going to be a weird definition. Concentration, well, not weird, just kind of vague. Concentration of a substance. And the units are going to be amount per meter or per distance. Amount per distance, I'll even say. The amount per distance. So, for example, it could be something like kilograms per meter. It could be something like moles per kilometer or whatever. It's just going to be like the amount, and it's going to be the concentration, the length density. So the amount per distance, amount per meter, kilograms per meter, something like that. It's just going to be the linear density, the linear concentration of the substance. Okay, we'll get to the basic assumptions in just a moment. But what we're going to have is I'm going to rederive this, but this is just going to be the continuity equation that we talked about way back in the beginning of class. So let's say this is going to be our one-dimensional thing. We kind of go off to minus infinity that way and positive infinity that way. This is just one little piece that's sort of going to model what's happening here. And the constant or the amount of mass in the interval a to b, I'm going to call this m of t, is going to be the integral from a to b u of xt dx. And I want to be careful with the units here. So what are the units for this? Well, this is going to be, let's just say it's measured in kilograms. So the units here would be something like kilograms per meter. This has units of meter. So overall, this has units of kilograms. Okay, and if I take a derivative, I have a derivative here on the outside. Well, now, if the integral has units of kilogram, then this is going to have units of kilograms per second. Okay, and it's just how much the mass is changing in that segment from A to B, how much is changing per time. It's just the derivative, the time derivative of the change of mass on that subinterval A to B. Okay, well, how do things change? By conservation, it's only going to change if we have mass flowing in here or out there. So it's just going to be the amount of mass flowing in per time minus the amount of mass flowing out per time. And this is what we call the flux density. So f of xt sorry, just the flux. This is what we call the flux. And it's going to be the amount flowing per unit time, so I'll just say per second, at time t and location x. Okay, so far this is just a rederivation of the continuity equation that we use for first order equations. And so what we're going to have here, it's going to be rate, and it's to the right. It's flowing to the right, okay? So amount flowing to the right. Okay, so it's going to be rate in minus rate out. Well, if things are flowing to the right, rate in is going to be F of AT, and rate out is going to be F of BT. Okay, and again, this has units of, we can see up here, this has units of amount, we'll say, so kilograms, we'll say, per second, kilograms per second, so units match up. And then we're going to do the thing that we did again from the first couple of weeks of class. This is going to be the integral from a to b of minus the x derivative of f. Okay, and now again, f has units of kilograms per second. When you take a derivative, you get units of kilograms per second per meter. And then when you multiply by dx, you just get kilograms per second again. Okay, so in other words, the units match up. Okay, furthermore, the bounds here don't depend on t, so I can move the integral on the inside. Okay, so this is true for every value, for every interval a to b. We have the t derivative of u. The integral of the t derivative of u is equal to minus the integral of the x derivative. So our conclusion, sorry, the x derivative of f. So our conclusion is that the t derivative of u is equal to minus the x derivative of f. And again, we've already done this. We've already seen this when we looked at first order equations, first order conservation equations in the first couple of weeks. We got this exact same equation. There we had something like f was equal to u times the velocity or something like that, and then we found a formula for the velocity. That's what we did sometimes. Sometimes you just left it as a generic function of u. Sometimes, you know, I said you could have a different equation for the velocity and have Euler's equations or something like that. Okay, a lot of that stuff is going to be related to what we're talking about today. But anyway, this is sort of the base equation that we're going to work with, that any substance that satisfies conservation of mass, which I would assume is most of them, is going to satisfy. Now, what makes how we specialize to diffusion is we're able to figure out what F is in terms of U. And this is what we're going to talk about here. So the basic assumptions are that the quantity, whatever it is, sorry, not the quantity, the substance, obeys Fick's law. Or Fourier's law. I'm just going to call it Fick's law. Okay, so what does this mean? Well, we're going to have these assumptions. One is going to be if concentration is constant, there's no flow. Okay, so again, food coloring in a glass, if it's the same concentration everywhere, the food coloring is not going to be moving. It's not going to be going, there's not going to be, you know, all of a sudden an area where there's no food coloring or less food coloring or something like that. If the concentration is not constant, the quantity, the substance, flows from higher concentration to lower concentration areas. Sorry about that. Okay, the bigger the difference between high and low concentrations, the bigger the flow. So bigger the difference in concentration, the bigger the flow. Okay, sorry, I just got a weird phone call. The bigger the difference in concentration. So the bigger the difference in concentration, the bigger the flow. And finally, different materials have different materials have different flow rates. And this is even if the concentration differences are the same. So, for example, if you have a puddle of water, little puddle of water on your desk or something, and you get a napkin and you touch it to the corner, and you get your, let's say, your shirt, and you touch it to the corner, the amount of the speed with which the water flows into your shirt or the napkin is going to be different for the shirt and the napkin, even though the concentration differences are the same. Okay, so all of these assumptions lead us to Fick's law, or Fourier's law. So Fourier came up with it for heat, I think, and Fick did it for more general diffused quantities that diffuse. And it says the following. It says that the flux is equal to minus a scalar times the derivative of u. Okay, so let's think about this. So let's imagine I've got, again, this is going to be like a pipe here. Whatever the substance is flowing in, will go off that way, and then we'll go off this way. And let's imagine that right here we have a very high concentrated area, and here we have a very low concentrated area. Okay, so what's going to happen? So let's think about u. U is concentration, so this means the derivative of u has to be positive. So I'm trying to explain the minus sign. Okay, the derivative of u has to be positive. But the flux is going to be pointing to the left because it's going from high concentration to low concentration. Okay, so the sign of the flux has to be opposite the sign of the derivative, because if the derivative is positive, that means concentration is increasing, which means the flow is going to go that way. Okay, that's by the item number 2. How does the derivative come involved? Well, the bigger the difference, the bigger the flow. So the derivative tells us what the difference in concentration is. That's one way to tell us what the difference in concentration is. Like if I look at this point right here, and I call this point x, and I call this point here x plus delta x, then the difference in concentration of those 2 points by the mean value theorem is going to be the x derivative of u evaluated at some point c in between x and x plus delta x times delta x. Okay, this is just what calculus says. So this is what the difference is going to be. Okay, so the higher the concentration, the bigger the difference in concentration, the bigger the flow, and so that gives us Fick's law here, which says that the flux is equal to minus alpha times the derivative of u. Okay, so I'm going to erase this, and let's talk for a minute about units, because as you might see, the units of f and the x derivative of u do not match up. So what are the units of f? Well, remember, this is going to be the amount per second. I'll just say kilograms per second. Kilograms, it could be moles or something like that. Okay, so what is this? Well, u has units of kilograms per meter. So what are the units of the derivative of u? Well, think about the difference quotient. It's going to be delta u over delta x. Delta u has units of kilograms per meter. Delta x has units of meters. So it's going to be kilograms per meter, or kilograms per meter squared. Okay, well now this tells us what units alpha has to have. Whoops. Come on now. This tells us what units alpha has to have. So for these units to match up, alpha has to have units of meters per second. Because now if I figure out the units over here, you're going to end up with kilograms per second. Or sorry, I guess this would be meter squared per second. So this has units of meter squared per second, because when you do meters squared, they cancel with those meters, and you're just left with kilograms per second. Okay, so that's what Fick's law says. And now, for the diffusion equation, I'm going to begin with the two equations that we just got. So the t derivative of u is equal to minus the x derivative of f, but I know f is equal to minus alpha times the x derivative of u. Okay, and of course I can combine these into one equation, and what I'm going to get is the t derivative of u is equal to minus the x derivative, and what is f? F is minus alpha times the x derivative of u. Okay, and alpha could be a function of x. I could have the medium through which this diffusion is happening could be non-homogeneous. And so alpha could vary with the location. So if alpha is if alpha is a function of x, so if alpha is a function of x, then the most simplifying I can do here is just to pull out the minus sign, and it's going to cancel. The two minus signs are going to cancel, and you're going to have the x derivative of alpha times the x derivative of u. Okay, if alpha equals a constant, we can pull that out of all of the derivatives, and we get what's kind of known as sort of the simplest diffusion equation, I guess. The t derivative of u is equal to alpha times the double x derivative of u. And this is really what people mean when they say, this is really what people are probably talking about when they say the diffusion equation. Okay, so I want to point out a couple of things here. One thing is that this is a second order equation. There are two x derivatives, which is why we call it a second order equation. The other thing that I want to point out is that so far, what is causing, in our model, what is causing, what is the thing that is causing the substance to move, right? It's here, and then it moves. Okay, we're assuming only, right now we're assuming only diffusion is causing movement, or I'll say change in concentration. Now compare this to the very first couple of weeks when we looked at the conservation law. The only thing there that we assumed was causing the substance to move was going to be some external velocity field, and we didn't really worry about the internal interaction of the particles. Here it's the opposite, where we're assuming there are no outside sources. We just have something like food coloring in a bowl. We're not mixing it or anything. It's just in there, and we're going to see what happens as it diffuses. Okay, in several videos, we're going to see what happens when we combine both of those things together, but not yet. We're first going to look at some properties of this PDE.